this music computer is so interesting that you could leave me alone with it a whole night long. These were the words of Herbert von Karajan when I presented to him the machine in Salzburg. This music computer was built in 1980 at the University of Zurich for investigations of classical music by modern, mathematically oriented methods. One of the main applications was a deep analysis of Beethoven's Hammerklavier Sonata. Recently, the use of the machine has been extended to brain research. We found new results concerning the correlation of listening to music and feelings within the human brain. Let me now explain the 5 components of the music computer. First, you have the central processor unit, which performs the calculations and the memory tasks. It is accessible by a normal terminal. To perform particular musical operations, you have this peripheral board. Here you have the sound generator for listening to real tones. The quality is rather mediocre, but for our first tasks this was not very important. Last, you have here a large monitor showing each tone as a light point, like on a musical partition. Observe that on horizontal lines you have tones of equal pitch, whereas on vertical lines you have tones of equal time attack. Let me now explain how the machine works. First, you put into the peripheral board tone by tone of a given musical piece. You have 88 pitches at your disposition, like on a piano. Second, you have 88 attack times at your disposition. And finally, you may choose to each tone an individual duration. Here I choose the octave. Here I choose the name of the tone. Here I choose the duration. And here I choose the time of attack. Now the tone is ready to go onto the screen. And I put in a next one. And the next one. Suppose now that we have memorized some bars of the Hammerklavier Sonata. Here they are. Of course, you may vary the loudness, the tempo, and the sound color during a performance of such a piece. But the most beautiful task which this computer may perform is the geometrical transformation of a piece of music on the monitor. Look at the music you just heard. We reflect the points a horizontal line. This is the classical pitch inversion. Here is the reflected configuration. And now we reflect at a vertical line. This is the classical retrograde, that is time inversion. Here it is, and listen to it. More generally, we may perform all classical affine transformations of the plane, like translation, reflection, rotation, or transvection. Look at the first bars of the Hammerklavier Sonata. Here they are. Now we translate -2 in the pitch direction and +6 in time direction. Listen. Now we perform a rotation of 45 degrees, followed by a dilatation of square root of 2. To the question whether this still is Beethoven, Herbert von Karajan answered, no, but it still sounds fascinating. These transformations may help to discover hidden symmetries. Look at this portion of our sonata. A translation of 17 units to the right and a vertical transvection give this picture. In fact, this melodic zigzag here and here is the germ of all melodic structures in our sonata. If Beethoven was so successful in using hidden symmetries to invent his marvelous music, why shouldn't we try to draw agreeable music by use of simple symmetries? Look at the following trivial example. What you see here is made of small triangles like this or this in an ornamental arrangement. In fact, every ornamental configuration has a good chance to sound reasonably, and vice versa. in every portion of good music there is a large amount of hidden symmetries. But there are problems where symmetries are very difficult to be discovered. Such a problem is modulation, that is, the passage from one tonality to the other. By use of mathematical models, the problem of modulation can be solved up to the point that the computer can perform modulations automatically. This is the model of a tonality. It represents a Möbius strip. Observe these 7 vertices, which represent the 7 steps of a tonal scale. If you want to modulate from one tonality to a second, you have to calculate the fundamental chords which have the force to leave the first tonality and to reach the second one. This calculus shows you this structure in the case of modulation from C major to F major. By simply connecting the 2 scales with this model, you get a configuration by which you may calculate the fundamental chords to pass from C major to F major. If you reverse the direction, you go from here to here, you get the modulation from C major to G major. This is the reason why you have here 6 models of modulation for all changes of tonality. Now listen to all these modulations performed by the music computer. Observe that each modulation is realized within 2 tones of extra long duration. Now we reflect horizontally. These are exactly the modulations between minor tonalities. And of course, this also follows from our previous calculations. But in order to perform all these modulations, you needn't know any musical or mathematical theory at all. To conclude, let me just present 2 examples of more sophisticated musical composition problems which are easily solved by the present computer. First, you see the structure of a rhythmical modulation calculated by simple rotation of the pitch axis into the time axis. Last example is a chain of suitably deformed 12-tone rows. To make more evident the internal structure, we enriched the composition by arrows at important points, and we performed a suitable geometric transformation on the whole. Now I get the enriched version from the memory. Here it is. What you see here in the inner field is the deformed row chain. And here are the deformed arrows, everything under a suitable transformation. Listen again.